Now we're going into the stoichiometry section. For stoichiometry, you have to have a chemical equation. So this one says sodium phosphate, Na3PO4, is reacting with iron 3 chloride, so that'd be FeCl3. We know that one of the products is iron 3 phosphate. It says so right here. So it'd be FePO4. And the other product then has to be the other two ions, which would be sodium and chlorine. Sodium and chlorine. The iron is +3, the phosphate's -3, so that formula is correct. That's a +1, that's a -1, so that formula is correct. Now the only thing that's left to do is balance the equation. There are 3 sodiums, so we're going to put a 3 over here, which gives us 3 atoms of chlorine as well. Turns out there are 3 over here, so we're finished with the balancing. In stoichiometry, you'll remember there are 3 steps. Step 1, change to moles. Step 2 was the mole ratio. Step 3 is change to grams. I'm going to say change to units. Often they're grams, sometimes they might be liters. All right, so number 1 thing to do, change to moles. You got 325 grams of iron 3 phosphate. So grams on the bottom. I'm expecting you to know how to write the formula for iron 3 phosphate. Remember that. Okay, moles of iron 3 phosphate here. 1 goes to moles. I have to add these up on the side, so I'm going to say out loud what I'm adding. Iron is 56, and multiply that by 1 because there's only 1 atom of iron. I'm going to add to that phosphorus, which is 31. And then I'm going to add to that 16 times 4 because each oxygen is 16. But there are 4 atoms of it. So I get a total of 151 grams. All right, now the next step is mole ratio. In stoichiometry, it's important to write what you're dealing with. So moles of FePO4 are on top. Moles of FePO4 go on the bottom. Moles of what you're looking for goes on top. What you're looking for is iron 3 chloride. So moles of FeCl3. Turns out in this equation that there's a 1 in front of the FeCl3, a 1, and there's a 1 in front of the FePO4. So it's just 1 to 1. Okay, I'm going to go ahead and do the third step down here. Moles of FeCl3 need to go on the bottom. Grams of FeCl3 will go on top since you are looking for how many grams. You might say, what is the mass? That would mean the same thing. So if I use 35 for the weight of chlorine, I multiply that by 3, gives me 105. I need to add the weight of iron of 56. So I'm going to have a total weight of 161 grams of iron 3 chloride. So I'll just do the math and make sure that I did it all right. That's 161 grams per every 1 mole. All right, so you got 325 times 1 times 1 times 161. Then I'm going to divide that number by 151. And I get 346.5. And I said the answer is 347.5, and I suspect that's because I may have used 35.5 for the weight of chlorine, so that's close enough. So I get 347, we'll say, grams of FeCl3. Next question. Using equation 6, if you have 125 grams of iron 3 chloride, how much salt could you make? So you have 125 grams of FeCl3. Change that to moles. Grams on the bottom this time, moles on the top. 1 mole, the number of grams we said was 161 grams of FeCl3. Better write down what we're dealing with. Now moles of FeCl3 go on the bottom. This is the mole ratio step. Moles, what you're looking for, goes on the top, and that would be NaCl. So that's, in this case, that's 3 to 1. So you look up here, see that 3 NaCl for every 1 FeCl3. For every 1. Okay, now we have moles of NaCl, but we need to know grams. So we're going to put moles of NaCl on the bottom. We're going to put grams of NaCl on top. And that's 58.5 or just 58 grams. So now doing the math, you have 125 times 1 times 3 times 58. Then I would divide that number, which was, I got 21,750, divided by 161. I get 135. And that's what I said the answer was. So there you go. Okay, now the decomposition equation I gave you. How many grams of hydrogen peroxide must be decomposed to make 5.5 liters? So you got 5.5 liters of oxygen. You're going to change that to moles. Put liters of oxygen on the bottom, put moles of oxygen on the top. 1 is 22.4. Okay, then you got to do a mole ratio between what you're looking for and what you have. You're looking for grams of hydrogen peroxide, so I'm going to put moles of hydrogen peroxide first. Then moles of oxygen on the bottom, because that's what's up here. Now the numbers are, there's 2 moles of hydrogen peroxide for every 1 mole of oxygen, so 2 to 1. Then it wants to know how many grams, so I'm going to have to go moles of H2O2 on the bottom, grams of H2O2 on the top. Turns out there are 34 grams in 1 mole. So your math on this one is 5.5 times 1 times 2 times 34 equals, divided by 22.4, and I get 16.7. Oh, son of a gun, that's what I said the answer was. 16.7 grams of H2O2. And by the way, if you're wondering, there should be a 1 right there. All right, I'm going to fly right into the gas law section as well. So here we go. Gas law section, there are 2 ways to do it. I'm going to do problem 13 one way, do problem 14 the other way, and I'll let you do 15 on your own. So here's 13. Either way you do it, you can say T1, T2, P1, P2, V1, V2. So in the first one, the volume 1 is 800 milliliters. Pressure 1 is 5 atmospheres. Temperature 1 is 200 K. Remember, these temperatures, all gas law problems have to have temperature in Kelvin. Come on. Someday I'm going to learn why it does that, but I haven't figured that out yet. I got 5 atmosphere. And temperature T1 is 200 K. T2 is 400 K. P2 is 10 atmospheres. V2 we don't know. So you start with your 800 milliliters. You know that temperature is going up, so that should make the volume get bigger, so you'd put 400 over 200. You know that pressure is going up, so volume should get smaller, so you'd put 5 over 10. That'd make the volume get smaller. So 400 divided by 200 is 2, but 5 divided by 10 is a half, so they cancel out. You multiply everything across the top, multiply everything across the bottom, but this factor cancels that factor because this doubles and that halves, so you get no net change. Final answer is 800 milliliters. All right, number 14, a different way to do it. You could say T1 V2 P2 equals T2 V1 P1. You'll still need to make your chart of T1, T2, P1, P2, V1, and V2. Okay, so you still need to do that. So V1, let's see, T1 would be 300 K. T2 was 300 K. That means you're going to be able to just leave that out over here if you want to, because they're the same. Okay, P1 was 6 atmospheres. P2 was 4 atmospheres. V1 is 400. So 6 atmospheres and 4 atmospheres. Okay, V1 was, what was I say, 400? All right, so let's go ahead and plug them in. T1, what did we say it was? 300 K. V2, we don't know, X. P2, we know, is 4 atmospheres. T2, we know, is 300 K again. So really, I could have left those out. They're just going to cancel out 300 divided by 300. V1, 400 milliliters. That's volume 1. And pressure 1, 6 atmospheres. So now to do the math, this times this times this, then you divide by 4 and divide by 300. Final answer will be 600. I'll just double check it. So 300 times 400 times 6. Then I'm going to divide that number by 300 and divide again by 4. Final answer 600, so I'm right. Okay, I'll let you do number 15 on your own. Number 16. Don't have to do all these, but these are all basically the same. So I'm just going to do one down here. So PV equals nRT. These are ideal gas law problems. Just doing number, I'll do D. So D has 0.5 atmospheres for pressure. It has a volume of 629 milliliters. But the volume has to be in liters. So you have to divide that by 1,000 to get the volume in liters. So be sure you pay attention to that. N is 0.0337. Since the unit of pressure is in atmospheres, we can use 0.08205 for R. I'm running out of room to write over here, so I can't put it all in there, but it's liter atmospheres per mole Kelvin. Then you have T down here you're trying to find. So you're going to have 0.5 times 0.629 divided by 0.0337 divided by 0.08205, and T will equal 114. All right, so I'll double check that math again. So 0.5 times 0.629 divided by 0.0337, then divide again by 0.08205. Final answer is 113. That's what I got. I got 113.7, which is 114. All right, I'm going to stop there and save this file so it doesn't get too long.